The classical idea of probabilities relies on calculating ratios of scalar quantities. And this idea can be used in many interesting ways. As an example, let's say I have a rectangular region enclosing an area A. And through a randomly drawn curve, I've divided it into two parts with an area that I need to figure out. So I do not know what is the area A1 and I do not know what is the area A2. All we know is that A1 plus A2 will be equal to A. And one of the ways I can use probability to calculate the areas of these unknown parts is to take a large number of objects such as coins and randomly throw them within the perimeter of the region. Having done that, I can find out or count the number of times the coin lands in the first part, take its ratio with the total number of coins thrown, and that gives me the probability for us to find or randomly discover part 1. And this ratio this probability will be equal to the ratio of A1 to the total area of the region. Likewise, I can calculate Q, which is the probability for us to find part 2, and that will be the ratio of A2 divided by A. Notice, having defined the probabilities this way, the probability satisfies all the properties we require of a probability, which is the probability is less than equal to 1 and greater than equal to 0, and the sum of the probabilities of these two exclusive events is equal to 1. In the description of quantum states, we need to figure out a slightly different way to introduce the idea of probabilities. Now, if you recall the experiment or the simulation of the experiment we did in the previous video, you saw that there is a profound difference between classical logic and quantum logic. And in order to explain the findings of quantum systems, we need a slightly different way of introducing probabilities, and that way is through vectors. Now, here is an example. Let's say we have a classical XY coordinate system and we have a unit circle. Now I can draw a unit vector, and this unit vector, let's say, makes an angle of theta with the x-axis. Therefore, it has a projection cosine theta along the x-axis and sine theta along the y-axis. Now, if I want to define probabilities, it needs to satisfy two very important properties. The probability of a quantity, even if it's a ratio of two scalars, has to lie between 0 and 1. And the sum of probabilities of all the events should be equal to 1. Given that the projection of a unit vector is cosine theta and sine theta or these projections themselves cannot be used as probabilities, even if we're talking about a unit vector. And that's because cosine and sine theta can take negative values, which is not allowed for a probability. Likewise, the sum of cosine theta and sine theta is not equal to 1. But here's the thing. Just using Pythagoras theorem, we know for this unit vector that cosine square theta plus sine square theta equals 1. And cosine square theta lies between 0 and 1, and likewise sine square theta. Can we use this idea of taking projections of unit vectors along its basis vectors, along its orthogonal basis vectors, squaring them, and use that as probabilities? Unlike classical states, which are completely well described by sets of values combined with logical propositions, quantum states, with all their inherent randomness and peculiar logic, are described by the language of vectors. And the way this randomness or these probabilities enter the description of these quantum states is through projections of these vectors along an orthogonal basis directions. For example, what we saw in the last slide, I have a unit vector and we know that its projections along the x and y direction is cosine theta and sine theta, and the square of those projections, cosine square theta and sine square theta respectively, satisfy all the properties we require to define a probability. So for instance, I can say that cosine square theta is the probability for me to be along the x-axis. Sine square theta is the probability for me to be along the y-axis. This idea can be generalized to an arbitrary unit vector in, say, n-dimensional space. And suppose we have an orthogonal basis vectors, which are generalizations of the coordinate systems that you just saw, x, y, z, expanded all the way to n dimensions. let's refer to these basis vectors as b1 hat, b2 hat, bn hat, and the components of this unit vector v hat along each of these directions as v subscript 1, v subscript 2 all the way to v subscript n. Then, since this is a unit vector, I can define a probability through the modulus squared of these components. So for instance, probability to be along the first basis direction I can say is modulus of v1 square. Probability to observe or be along the second basis direction as mod of v2 square, and so on all the way to mod of vn square. Notice, having defined probabilities this way, it satisfies all the properties we require of a probability, which is the modulus squared of all of these components is less than equal to 1 and greater than equal to 0, and being a unit vector, the sum of all of these modulus squares is equal to 1. Quantum states are thus vectors whose components square to give us the probability to observe different values along these different basis directions. More on this in the next video.